Question A asks us to identify the limiting reactant when the methane and chlorine gases combine, and to calculate the total number of moles of CH2CO2 in the container after the limiting reactant has been totally consumed. We can solve both of these problems by doing stoichiometry. If you convert the moles of reactants to moles of CHO2, we will take the lowest amount of moles calculated, and that reactant will be the limiting reactant. In the problem, we are given 25 grams of CH4. To convert that to moles, we divide by its molar mass of 16.05 grams. Then we use the coefficients in the balanced chemical equation as a ratio between methane and the CH2CO2. And as you can see, it is a 1:1 ratio. We end up getting 1.56 moles of CH2CO2. The problem also gives us 2.58 moles of chlorine gas, which we can convert to moles of CH2CO2, also using the coefficients in the chemical equation. And for every 1 mole of dichloromethane, there are 2 moles of CO2. So we divide the 2.58 moles of CO2 by 2, and we get 1.29 moles of CH2CO2. Since 1.29 is clearly smaller than 1.56, the CO2 is the limiting reactant. Question B asks us to calculate the number of moles of each of the revolving reactants before the reaction begins. The problem gives us 75.0 grams of iron. To get this into moles, we have to divide by its molar mass of 55.85 grams, and we end up getting 1.34 moles of iron. The problem also gives us 11.5 liters of O2, 2.66 atm, and 298 Kelvin. To find the moles from these numbers, we have to use the ideal gas law, which is PV equals nRT. We can modify this equation to get moles equals pressure times volume divided by 0.0821 times the temperature. And the R comes from the molar volume at STP. So we multiply 2.66 atm by 11.5 liters, and we divide that by 0.0821 and 298 Kelvin, and we end up getting 1.25 moles of oxygen gas. Question B also asks us to identify the limiting reactant when the mixture is heated to produce Fe2O3 while showing calculations. Firstly, we take the 1.34 moles of iron I calculated previously and convert that to Fe2O3 using the coefficients in the equation. And for every 4 moles of iron, there are 2 moles of Fe2O3. So we end up getting 0.67 moles of Fe2O3. Now, take the 1.25 moles of O2, which we also calculated in the previous slide, and convert that to Fe2O3 by once again using the coefficients in the chemical equation. And for every 3 moles of O2, there are 2 moles of Fe2O3. So we end up getting 0.833 moles of Fe2O3. And since 0.67 is smaller than 0.833, we can conclude that iron is the limiting reactant in this problem. So in this problem, we use the equation N equals PV divided by RT. And you know what P stands for pressure, V stands for volume, and T stands for temperature. But what does R equal? Well, if we modify the equation, it is R equals pressure times volume divided by moles and temperature. So at STP, the standard pressure is 1 atm, the standard volume is 22.4 liters for a gas, and the average mole is 1 mole at STP, and the temperature is 273 Kelvin, and we end up getting 0.0821, which is the number we used in this equation.